Hello, my student. This is a clip that I'm going to demonstrate to you how to solve to determine the deflection of the beam by using the superposition method. We did study the superposition method since we take the mechanics of materials, and we also have the final examination on the mechanics of material, if you remember. So now the problem is a little bit more comprehensive than the one that we have in the mechanics of material. Let us consider the simply supported timber beam subjected to the loading as shown here. There is two types of loading. One is the point load, that is 12 kilonewton, and the other we have is the 2 kilonewton per meter, that is the uniformly distributed load. The problem also gives us the equation for the deflection of the beam under this load, and we will use this table to compute the total deflection that occur on this beam. Okay, the beam has the rectangular section, and it states that the width is 100 millimeter, or the width is going to be 0.10 meter if you like to use this in meter unit. Okay, the timber has the modulus of elasticity of 4 gigapascal. That is quite low, 50 times lower than the steel. The steel has 200 gigapascal. Okay, and next they ask us for what? They ask us to determine the deflection at the midspan of the beam. So let us consider the beam. The beam has two loading, and the loading and the beam is not symmetry. This beam is unsymmetry. When the beam is unsymmetry, the maximum deflection may not occur at this midspan. So they ask us next to what? To check whether that obtained midspan deflection is the maximum or not. Okay, this is a kind of more than we have in the mechanics of material. And then let's check what? Check the maximum deflection with the allowable deflection, which is said to be span divided by 240. So that means this beam will not have wall under it. If it have wall, it's going to be span divided by 360. Okay, if it pass, that means the beam is stiff enough to resist the load. If not, we got to redesign this beam. Okay, so based on this method, we have basis on the principle of superposition. We have principle of superposition, and we have talked about it many times. Basis on this, there is two assumptions. If you like to follow this principle of superposition, first, under the force, under the load, the material or the timber in this condition is in linear elastic behavior. Okay, this is elastic behavior. And also the second, under the load, the deformation of the beam is very small. That's for sure. The deformation gonna check with this condition. Okay, the span over 240, and then for this, based on the principle of superposition, because the load 12 kilonewton and 2 kilonewton per meter, we can separate the beam into two cases. Okay, and then what we have is this beam gonna be separate. One gonna subjected to the uniform load, another one's going to subjected to the point load. So let me move this one a little bit up. We're gonna project this beam and we're gonna draw the shape of the beam, and then we will sketch the deflection. How long it is? It's gonna be 6.8. So this one gonna be 3.4. Okay, this one about 3.4. It's going to be the midspan. This is going to be the midspan. Let me mark this one. It's going to be the midspan of the beam. Okay, under the loading, what we have, the elastic curve. We should draw the elastic curve, okay, of the beam, and to show how you understand the problem. Since the force, most of them are near the B, so the slope here supposed to be larger than what? Larger than this portion. Okay, and since you know that, and then you can sketch the curve must be what? Must be continuously. Okay, must be continuously curved. Okay, it cannot separate because it's like the ruler. Okay, you can see the deflection going to be like this. It's always curved like this. Sometimes you may use this to draw the pictures. Okay, and what they ask us is to determine the deflection at this point, and let me call this is what? V at L over 2. Okay, that is going to be equal to two more beam over here. Let's has the one is subjected to uniformly distributed load, and another one gonna subjected to the point load. So we have this one, and we also have this. It's going to be plus, okay, because the combination of the load must be plus. And we have the pin and the roller as we have. And this time we have the uniform load is what? Uniform load is symmetry. Is symmetrical load. Since it is symmetrical load, what happened is under it, the beam will deform the rotation here and rotation here. What? Will be equal. And we will have this to be defects. And the maximum deflection will occur at the middle due to the symmetrical of the loading. Okay, and this is going to be what's so called V1. Let me call this V1, and then the slope here gonna be 0 because it's a maximum deflection is here, and then the curve gonna be like this. And the second one, this one, again, the load act over here with the 12 kilonewton. Okay, this one is 2 kilonewton per meter. So the rotation here gonna be bigger than this one. Okay, and the deformation gonna be some kind of have the maximum deflection allowed here, and then it's going to curve back, and the maximum going to be around here. But what we have is we have to determine the deflection at the midspan of the beam. So we call this V2. Okay, so from the graph, what we have, thus we have what? We have V at what? At L over 2 is gonna be equal to V1 plus V2. Okay, the deflection here gonna equal to this one plus this one. And then what is this one? this one is the point load, so it's going to be allowed here. What we have here is what we're going to determine the deflection at what, at the midspan of the beam. So the first thing that we have is the x, okay, the x, the position that we are going to determine the deflection. So x is, this is what, this is 3 meters. So at the midspan it's going to be 1.5. So x equal to 1.5 meter. And the L is going to be the total length. That is going to be 3 meters. And we have this for 2 kilonewton per meter. So we have this. We have x, okay, and we have L. Then we can input everything into this equation. So for the first one, this is going to be what? Equal to the V1, the V1 due to this is W, X, W is 2, that is 2000. Let's put it into Newton, okay, and X now is 1.5, so this is 1.5 meter, and then it's going to be divided by 24 EI, so divided by 24, and E, what we have, E is 4 gigapascal, so it's 10 power 9 Newton per meter square. And I, what we have, we don't have I yet, okay, the I of this beam is what? The I of this beam is going to be 0.1 meter, and the depth 3 times 0.1, so that is going to be 0.3 meter power 3, and then divided by 12, divided by 12. And if you put it into your calculator, you may get this one for 2.25 and 10 minus 4. And then the unit must be meter, okay, power 4, it's time meter. And then if you put it, you may get this one, 225, 10 minus 6 meter power 4. Okay, and if you put it over here, it's going to be 225 and time 10 minus 6 and Newton per square meter. Oh, sorry, it's it's going to be just it's an I. It cannot be like that. It's going to be the unit of what? Oh, this is the unit of something. I lost my mind. So powerful. Okay. And then what we have next, okay, is going to be x power 3. So that's going to be 1.5 meter power 3. And minus of what? Minus 2 time L. L is 3 meter. So time 3. And then x square is going to time 1.5 square. And plus L cube 3 power 3. Okay, that is the first one. And the next you have this. You have this. For the second one, you have this equation. And now again, we are determining the deflection here. So the distance we have for x equal to 1.5 meter. So that is the x. And then the L is the same. L is 3 meter. By considering the distance between the support and then the applied force, this is going to be 2 meters. So A is equal to 2 meters. And then the last one, B, is equal to 1 meter. By doing that, you can further your consideration, okay, with P. Oh, you don't need to put minus into the equation because we know already it's downward, okay? Keep it in your mind, it's going to be downward, okay? So the P is the P here. That is going to be 12 kilonewton, or you may put it 12,000 Newton. And then B, what B is 1 meter. You get this one for 1 meter. And then you get what? You get the X. The X is 1.5 meter. And the divider is going to be 6 EIL. It's going to be 6 times E times E. E is going to be 4 and E 10 power 9 Newton per meter square. And then you also have this one for E and I 2 to 5 and 10 minus 6 meter power 4. And then also L. L is going to be 3 meter. So you're going to put 3 meter here. Okay. Don't forget to put 3 meter here. So you will go further. Then what? L square. So it's going to be 3 square. And minus B square minus 1 square. And then what? Minus X square minus X 1.5 square. Okay. And if you trying to put in your calculator, you must be very careful with this. Okay. And the first one, if you put this one into your calculator, you will get it for, you may pause the video and try to do it by yourself. How much you get? That is going to be 10 minus 6. And then if you put this portion, okay, into your calculator, you will get it for 16.875. Okay, and then if you put this portion into your calculator, you may get this one for 111. Let's have 111, 1.111 and 10 minus 3. Okay, and the last one, if you put this is going to be easy. 9 minus 1. Okay, 9 minus 1 is 8. 8 minus 2.25. That is going to be 5.75. And then you get the result of this of equal to 0.00234 and then plus 0.00639. Okay, this is going to be in meter and it's downward. Like I said, we just put it in our mind. Okay, and you can see the deflection from the point load is about 3 times, nearly 3 times larger than the uniformly distributed load. Okay, and then later when we check the maximum deflection, you will find something. So by this one, you may get this one for 2.34 in millimeter plus 6.39, and the result you are going to have is in millimeter, and it's going to be downward. That is going to be what? 8.70. Is this 8.70 going to be the maximum deflection? I said, sometimes yes, sometimes no. And at this time, you may see the load is not symmetry. Okay, so what's going to be the next point that we should check with the maximum deflection to find the maximum deflection? Check with this to find the maximum deflection. Coming back to here, over here, the maximum gonna occur at the midspan, okay? And at the midspan, theta equal to 0. But for this one, according to this, the maximum deflection will occur between the midspan and the loading point. And so let us say this is going to be the point of midspan. And what is going to be the distance from here to here? Can we find this? Yes, we can find this. We can find it. Okay, we can find this. By what? By the condition that theta equal to 0. So what we consider is determine x dash produce produce Vmax for the second case. Let's check. Okay, let's check. So the theta is 0. That means we gonna to differentiate this equation. So we got to dv by dx, and then we going to diff this by dx. Diff what? Diff the equation here. So it's going to be pb, and then divided by 6 EIL. Okay, and then again you get this for what? For L square x is going to be L square x minus b square and x and minus x cube. Okay, and then after you do the differentiation, the first term will provide L square, the second term minus b square, and the third term will be minus 3x square, and this one gonna be equal to 0. Okay, and then if you rearrange the term, we are determine what? We are determine the x. So it's going to be 3x square. Let's say it's 3x square equal to, move this one up, equal to L square minus b square. So putting to this, we will have x equal to L square minus b square, this term, divided by 3, and then you're gonna have the square root of it like this. Okay, if you put further, you may get this one equal to the square root of L square. How much? L is going to be the length here, that's it's going to be 3 meters, so it's going to be 3 square, and then minus the b is over here, the b is here, the b is 1 square, and divided by 3. And if you put this into your calculator, you may get the x to be 1.633 meter. Okay, 1.633 meter. Then we suppose this is going to produce the maximum. Okay, and let us assume the deflection that occur here gonna be V2 star. Okay, the deflection here, and also it's going to make the deflection here. Let's call this is V1 star, and it's also produced. Sorry, let me take this one up here. The deflection here between this and this is going to be, let's say, V star. So next we're going to use the principle of superposition to what? To determine V star, and V star is going to be equal to V1 star plus V2 star. Okay, based upon the principle of superposition, we will get this. Okay, let me write this basis upon. Let me put this over here. On the principle of superposition, what we have is going to be V star is going to be equal to V1 star plus V2 star, and this time we just use the same calculation here, but this time you need to change 1.5 to 1.633 meter. Let me put this one is equal to 1.633 meter. Okay, to make it clearer. So it's going to have equal to 2000 Newton, and then let's put this one is 1.633 meter, and then it's divided by the same number there. Okay, this is going to be 24 times 4, 10 power 9, 225, and then 10 minus 6. And the order here, you got to change. Okay, 1.5 must be 1.633, and then cube and minus, okay, 2 times L. L is going to be 3 meter, and x square, this is x square times 1.633 square, and then it's gonna plus this one L cube, so 3 power 3. This was first term of this. This is V1 star, and then it's going to be plus with this one. Okay, it's going to be 12,000 Newton, and then it's going to divided by what? Divided by, no, it's on time B. This is B. This is X, so B is 1 meter. B is still there. But this 1.5 change to 1.633 meter. Okay, and then you're going to have 6 times 4. 6 times 4 and 10 power 9 and 2 to 5, 10 minus 6. And don't forget this one, that is 3 meter is the L. Okay, and then in parentheses you got this one, L square, 3 square, and minus B square. Okay, and then minus X square, 1.633 square, and then you get this. If you do this, you may get 2 portion of this. And again, if you go to compute slowly, you may get this one equal to the first part. The first part is going to be 1. This one is going to be 151 part point 204, and then 10 minus 3. 10 minus 3. It's 10 minus 3. 10 minus 3. Okay. 10 minus 6. 10 minus 6. 10 minus 6. 10 minus 6. And then it's gonna time what? Time this one. This number change. This is used to be this. When you put it, it's 15.354. 15.354. Okay. And next, when you put them together for this one, for this portion, and then you get it for 1.2096. 1.2096 and 10 minus 3. Okay, and the last one, when you put into this one going to be easy. It's going to be what? 5.332. That is going to be 5.332. Okay, and then you get the result of this is equal to 0.00232, and the other one you got is going to be plus for the point load. It's going to be 0.0000645. That is going to be meter, and it's downward. Okay, and if you make another conclusion, this one going to be 2.32 and plus 6.45, and then you will get this to be what? To be what? 8.77 millimeter. So this is going to be the Vmax. So thus we have Vmax equal to 8.77 millimeter. Okay, it's not that one, it's going to be this one. And the answer is going to be here, and it's going to put to in the downward direction. That is the answer that we have for the Vmax. Okay, and then we need to check. Okay, we need to check. We check the Vmax with the V allow. Okay, and what we allow, we have V allow is equal to the span L over 240, and this time we have is going to be 3000 millimeter divided by 240. That is going to be 12.5 millimeter. What we have is the V allow is larger than Vmax, therefore the beam is steep enough. Okay, steep enough in the case of no wall under the beam. If we have the wall, this is no wall. If we have the wall under the beam, V allow gonna be equal to L divided by 360. That is gonna be 3000, and then divided by millimeter, 360. That is going to be 8.33 millimeter. What happened is we allow less than Vmax of 8.77 millimeter. So this is going to be no K. Okay, in okay. Redesign the beam. We need to redesign the beam. To obtain what? Obtain a larger section. Okay, that beam going to be a larger section. Okay, that is all we have for this problem, and I think you guys may recall what we have previously in the mechanics of material, and you may see that this problem sometimes the maximum deflection occur at the midspan of the beam, but this one the maximum is occur here, which the value of 8.77 millimeter, but actually is close to this one of 8.73 millimeter. So sometimes they can approximate to use this one, but theoretically we as an engineer, we should check everything to make things are fine. Is our profession. Okay, that is a little bit more in depth than what we have in the mechanics of material, and I hope you guys will understand this and getting more knowledge, and let you practice some more problem to get more skill. Okay, that is the end of this script. Bye.